Okay. I'm sure you can see my screen now.
Yes, Nana.
Okay. So, we're looking at our last topic, test of independence, chi-square to be specific. Okay. So, by the time we finish today, you should understand what chi-square is about, complete a contingency table of expected frequencies. We'll learn how to compute the chi-square critical value, okay? And so determine the degrees of freedom for observing expected frequency table. Then test the independence of two variables, okay? So looking at, taking off from the last objective, if you have two variables and then especially when they are categorical variables and then you want to check whether they are related, there's some relationship between them. One of the ways to do that is to use chi-square, right? So chi-square helps researchers to understand relationship between categorical variables. So I don't need to go over categorical variables. I'm sure you know what it is by now. Okay. So it involves, frequency of events. Okay. We look at how events occur within categories, and then we compare the two to see whether there is a relationship. Okay. So here we look at observed frequencies as well as expected ones. Okay. And then it helps us to assess that. It helps us to determine the rule of random chance variation between categorical variables. So when we look at two, let's say, categorical variables, we can say that, okay, this change that is happening within them is as a result of the variation that is happening within them is as a result of random chance. Or could it be that there is something more than chance happening? All right. Okay. So it helps us to do that. So in effect, I mean, we start with establishing our hypothesis. So in the end, we reject the hypothesis or we fail to reject the hypothesis. So that's why I've put the accept in quotes. Okay. All right. So let's start with an example, as always. Okay, so that you can put this into context, right? So assuming someone has two dies. So one is a fair die and one is a loaded die. Okay, so when we say a loaded die, that means that the weight on that particular, so a die has six sides, isn't it? So it is said, I don't know how far it is true, okay? It is said, especially for those who gamble, they go to the casino, they have dice and stuff like that. And it is suggested that, I'm not a gambler, so I don't know how far it is true, but it's been suggested that, the dice that they normally use in the casinos, it is not a fair die, it is loaded, okay, for a particular side to show. Okay, so they know how they manipulate it. Okay, so let's say if a die, the weight has been altered a bit, that shows, let's say 156, for instance. That means that most of the time when we throw it, okay, it's going to show either 1, either 5 or 6 instead of the others, either 2, 3, and 4. It will not show, but the loaded ones will show. Okay, so so this is a scenario we have. So we have one die that is fair, we have one die that is not fair, that is loaded. Okay, so you are given one die and asked to determine whether it is fair or loaded based on a 95% confidence level. Okay, So over the next 6 days, you are required to roll the die 100 times for a total of 600 rolls, and then record how many times each number occurs. So basically, if everything is fair, theoretically speaking, then what will happen is that for each of the numbers, we are going to get 100, isn't it? If you are going to throw it 600 times, then it is expected that theoretically, okay, it is expected that if the die is fair, if the die is fair, then we can infer that theoretically each number will show up 100 times. Please, do you agree with this assertion?
Yes, Nana.
Okay, all right. So if the die is fine, then we are expecting a frequency of 100 each. Okay. So let's start with our hypothesis that, okay, the die is fair. Okay. And then our alternative hypothesis is that the die is not fair. So what we want to see is to test this hypothesis. Okay. And then see whether there could be any variation in the observed data, okay, or there is not. Or even if there is variation, is it simply as a result of chance or something that goes beyond chance? Okay. So now we say that we are using a 95% confidence level. Okay. So we are giving room of error for 5%. So our p-value is up to 0.5, okay, or 5%. Okay. So since the die has 6 sides, our degree of freedom will be 6 minus 1. Okay. Remember, I explained degree of freedom the last time. Okay, so it's n minus 1. So here we are having 6 minus 1. Okay. So if you are to check this on a typical Excel, okay, we use the chi-inverse in Excel, okay? It will open up this for you. It will open up a dialog box. We will have a practical session, okay? It will open up a dialog box, and then you enter the error, okay? The error and also the degrees of freedom, okay? However, the chi-square has its own distribution table. So let me use that quickly and then we'll explain. I've sent the distribution table, so have a look at it and then let's all go through it together. Please, have you seen it? I've sent it on the platform. I don't know whether you've received it yet. So have a look at it whilst also. Okay. Yeah, Nancy, just a minute. Okay. Yeah, Nancy, yes, you were asking a question.
Yeah, I'm sorry, Nana. I don't mean to drag you back, but I'm having a few network challenges. Would you mind repeating yourself, please?
Okay. Okay. No problem. So let me see if I can get is it raining at your side? Raining.
No, Nana, it's not raining.
Okay.
My network is just really bad today.
All right. Okay. So you are okay to the point where we spoke about the expected frequency being 100 each. Are we okay with that?
Yes, please.
Okay.
So right after when we were agreeing that each number would probably appear 100 times.
Yes. Okay. So we want to test this. Okay. In a typical hypothesis. So are you seeing my screen? Are you seeing
Yes,
the
please.
hypothesis? Okay. So our null hypothesis is that the die is fair. Okay. And then our alternative hypothesis here is that the
Yes,
die is not fair. Okay. So what we want to do
the
is
die
that,
is not fair.
so we want to find out, is the variation in our observed data simply due to chance or something else? Okay. There's something that goes beyond random chance. Okay. Right. So we have more information here. We are using a confidence level of 95%. Okay, which means that
Okay.
we are giving room for error of
Error.
5%. Okay, so our
Okay.
error probability is 5%. Okay, and since a die
Okay.
has 6 sides, our degree of freedom will be 6 minus 1, which is 5. Okay.
Okay.
Okay, right, good. So here, I was saying that the chi-square critical value is 11.07. How do we get the 11.07? Let's go to, before we go into Excel, let's go and use the distribution table, which I have sent to you. So download the distribution table that I put in the on the platform. Okay.
Okay.
So can you see the distribution table?
Yes, Nana.
Yes, sir.
No, I'm saying like on Zoom. Can you see it?
On your
Yes.
screen?
On my screen, you can see it.
Yes, yes, yes.
You can see it.
We can
Okay.
We can see it.
Nana.
Okay. So based upon what we've done already, just move to, you see on the left-hand side, you have the degrees of freedom. Okay. So in this case, our degree of freedom is 5, isn't it? So you come to the 5th degree of freedom. Okay. And then we are using an probability error rate of 5%. So we have 0.05. Okay, so if you read the 5th degree of freedom, you see that we have 11.07. Can you see it?
Yes.
Yeah. Okay. So for an error rate of 5% and a degree of freedom of 5, okay, our chi-square critical value is 11.07. So when we do our calculations and then it goes beyond 11.07, then we will reject the hypothesis, isn't it? This is outside the region, so we'll reject the hypothesis. If it is within it, is within it, then that's fine. We'll fail to reject, just like we've done for the other readings we've done in the past. Are we all okay with this? Or should I go over it? Hello?
Kindly go over, Nana.
Okay. So we have, how many degrees of freedom do we have so far? It's 6 minus 1, which is 5, isn't it? So the die has 6 sides, okay? So we have 6 occurrences, 6 possible occurrences. And since we are using a degree of freedom, it's always n minus 1. Okay, I explained that last time. So the degree of freedom in this sense will be 5. So when we take the chi-square distribution table, okay, you go to the 5th degree of freedom on your left hand side, okay, and then we are using 0.05, the error rate, okay, our alpha is 5%, okay, so you go to where 0.05 is, and then you read down to the line of the degree of freedom that you are using. In this case, our degree of freedom was 5. So when you read down of 5%, okay, 0.05, you come to 11.07. So this is what we call our chi-square critical value. Is that okay?
Yes.
Okay. So when you come here back to the table, okay, you will see that we have our chi-square critical value. Okay, so therefore, if our chi-square critical value, our chi-square that we are going to calculate, if it is more than 0.07, then okay, we must reject the null hypothesis and conclude that the die is not fair. Is that okay? Because that would be our alternative hypothesis. All right? The SL will come to the SL later, okay? But for now, when you read from the table, all that you need to do, first of all, establish your confidence level. We know our error probability, okay? Establish your degree of freedom, and then you can read the critical value, the chi-square critical value from the chi-square distribution table, which in this case is 11.07, okay? So once we've established this, we are going to work out the actual observed occurrences. And then when we calculate the chi-square, whatever figure we get, if it is more than 11.07, then we reject the null hypothesis, okay? And then conclude that the die is not fair, okay? All right, so let's see. So our expected frequency was 100 for each number, okay? So we have now established that when you actually threw the die, in the first instance, we were expecting, we were talking in terms of theoretical terms that if the die is fair, 1 to 6, and then you throw it up and up 600 times, then each of them will have 100 each, okay? But actually, when you threw the die, for number 1, you threw it 111 times. Number 2, you threw it 90 times. Number 3, you threw it 81 times. 4, 102 times. 5, 124 times. 6, 92 times, all making 600. So the observed or your actual throws, these are your actual throws. And then the one on the left were your expected throws, okay, theoretically. Please, do you get a difference?
Yes.
Okay, so we have expected frequency, and then we have the observed, okay? Observed frequency, if you could call it that way, okay? So what we do is that you deduct you deduct the observed from the expected, okay, which gives you this difference, okay? So when you deduct this observed and then the expected, it gives you 11, okay? It doesn't really matter how you deduct which one comes first, because we are going to square it, so it doesn't really make a difference, okay? Okay, so we have expected and then observed, all right? Okay, so O minus E, all right? So this one gives you 11, the other one gives you negative 10, okay? This one gives you negative 19, 2, 24, 8, all right? Then the next step is to square the difference, okay? So when you square the difference, for 11 squared, it gives us 121. Negative 10 squared gives us 100. Negative 19 squared gives us 361, and so forth. Are we okay up to this point? So we have our expected frequency, we have our observed frequency, okay? You find the difference and then you square the difference. Are we okay up to this point, please?
Yes, Nana.
Okay. Now, after you have done that, okay, then another column, you divide the difference by the expected value. So the expected value is 100. So remember that the square difference was 121, okay, for the first number. So if you divide it by the expected frequency of 100, it gives you 1.21, okay? And then The second one, the square difference was 100. You divide by the expected frequency of 100, it gives you 1. Okay. The third one, the square difference was 361. We divide by 100, that's the expected frequency, it gives us 3.61, and so forth. So when we finish, okay, when you are done with this, okay, you add them up. So you add, so this O minus E squared divided by E, okay, whatever you get, add them up. That gives you your chi-square. Okay, so here our chi-square is 12.26, okay, which is more than our critical value of 11.07. Do you remember? So here, on my right, on my left here, you see the chi-square formula. So it's the summation of the square difference divided by the expected frequency. Okay, that gives you the chi-square, our chi-square value. All right? So this is the actual chi-square. So you compare it with the critical value of the chi-square that you calculated from the T distribution, which was 11.07. So this will be our conclusion. The observed frequency for each number on the die differs significantly than would have been expected on a theoretically fair die, okay, where we have the degree of freedom was 5 and then number of observations 600, okay? So here we had 12.26 at a p-value of 0.05, okay? So our problem was, the problem chi-square was 12.26, okay? Our critical value, okay, for the chi-square, that is the probability error rate and also the degrees of freedom, gave us 11.07 from the distribution table, okay? So here we say that the variation was too great to be explained by chance alone. Therefore, we reject the null hypothesis that the die is fair, all right? Mathematically, you are expected to conclude like this, okay? So just practice and then make sure that you conclude your results like this so that it looks very technical, okay? So basically, what we've done is that you look at the expected frequencies and then compare it with your observed frequencies. Find the difference, square it, and then divide by the expected frequency. Whatever results that you get, you add them up. That gives you your chi-square. Okay, but before then, you would have established your critical value, okay, which is just the probability, okay, your alpha, and then your degrees of freedom, which you can easily read from the chi-square distribution table. Now, when you do it and then your actual chi-square that you calculated is more than your critical value, you reject the hypothesis. It is less than your critical value, you accept, or you fail to reject the hypothesis, so to speak. Is that okay? Any questions on this one? Any questions on this one? Any questions, please? Any questions? Any questions? Bridget, are you okay? Is Bridget here with us?
Nana, please, I'm here. Please, I'm okay.
You're okay. All right.
Yes.
Abdul, what about you? Abdul.
Then I've
Abdul.
just joined.
You
I have
just
just
joined.
joined. Yes, please.
Christiana, are you okay?
Please, I'm okay.
Okay, good. Emmanuel Labi. Labi, are you okay?
Yes, I'm okay, please.
Good, good. Delasi. Delasi, are you okay? Okay, Nana Ama. Nana, are you okay?
Hello, Nana. Sure.
Yeah, good.
Sure.
Okay. And then Nanefia, are you okay?
Yes, please.
Okay, right. So basically that is all there is about chi-square. So let's take more examples. Okay, let's take more examples and then we can work it. So let's assume the first one. Okay, so assuming that now our error probability will reduce p-value to 1%. Okay, reduce the error probability to 1%. Can you find from the chi-square distribution table? It's 15.09. Can you find out yourself? Look at the table and see whether you'll be able to read it and get 15.09. You know, if you don't understand it, then I'll go to the table and then explain. So go to the table and see if you can easily do that. Let's say our okay. So you go to the table and then do that. Let's say our confidence level is now 90%. Okay, let's assume that our probability is 10%. Read the chi-square critical value with the same information. Read the chi-square critical value from the table. Let's see. So when you read it, just let me know.
And I please the question again.
Okay, so if the confidence level is 90%, okay, or the error probability is 10%, okay, determine the chi-square critical value from the chi-square distribution table. If the degree of freedom is 5, everything stays the same, but we have just changed the p-value, okay? We have increased the probability, the error to 10%. What will be the chi-square critical value? Anyone? Okay. Melody, 9.24.
Nana, I'm getting 9.24.
You are getting 9.24. Okay. All right. Richard, 9.24. Okay. Right. Okay. So it's very easy to read it from the so 9.24 is correct. So in this instance, will you reject the hypothesis, the null hypothesis, or you fail to reject it? That the die is fair. Remember when we worked it, what did we get? We got 12.26. Do you remember? So,
Yes.
So what would be your conclusion? Will you reject the null hypothesis, or you fail to reject the null hypothesis? Hello? Any volunteer?
Nana, we will fail to reject.
You fail to reject. Okay. Why?
Because it's less than the,
Critical value.
yes, that's the 11.07.
No. Now, your critical value is 9.24. It's no longer. Remember now you are
Okay,
using
okay.
10%.
So it's the 12
Okay. So now,
point. Okay,
so the 12.26 is your actual chi-square
okay,
that
I
you've
get.
calculated. Okay. And then the critical value of the chi-square is now 9.24. Okay.
Okay.
So you will still go ahead and then reject the null hypothesis. So what you realize is that when the probability is decreased to 1%, okay, if the confidence level is now 99% and then the probability is 1%, do you see that we get 15.09? Please, you follow.
Yes, Nana.
Okay, so in this case, will you, supposing the scenario has changed, okay, we have just reduced the probability from 10% to 1%, okay, would you reject the null hypothesis, or you fail to reject it?
We'll fail to reject
Okay, why?
because the calculated chi-square is less than the one read from the table.
Okay, so this now becomes your critical value, isn't it? So the 15.09 now becomes your critical value. All right. So the effect of reducing your probability is that now you give more room. There will need to be more variations before you reject a particular hypothesis. Have you seen? Okay. All right. So, any other question? Any other question? So by reducing the p-value to 1%, we are going to need a lot more variation to reject our null hypothesis. Okay. So we've looked at a situation whereby we increase our p-value, okay, or reduce our p-value, okay, and then its effect, okay, on our conclusion, right? Okay. Any other question? Any other question? So you can try this on any Excel. You can, if you are not using the distribution table, okay, you can try in your Excel. Okay, just open up any Excel worksheet and then just type chi inverse error, and then so the first figure will be, it will open a dialog box for you. The first figure will be your probability, and then the second one will be your degree of freedom. See if you will get the same thing, the same answers that I'm getting here. Try it and let me know. So do it for when the do it for when the degree of freedom was 5, and then the probability was also 5, and also do it another one where the degree of freedom is still 5, but the probability was reduced to 1. Okay, see if you get 15.9. Okay, just open in Excel worksheet and then try it. You want me to also do it so that we all learn together. So let me open it. Can you see my screen?
Yes, now.
It's an empty worksheet, isn't it?
Yes.
Okay. Okay, so just bring equal to, and then chi. So it opens a lot of these for you. So choose the chi inverse. Okay. And double click that. So your first figure will be your probability. Okay, so let's say 0.05. Okay. And then your degree of freedom 5, for instance. Okay, and then you close the bracket. Okay, so you see that it's giving 11.5. Okay, let's try. So this one was for a degree of freedom. Okay. So let's say we have probability and then degree of freedom. So the degree of freedom is 5. Probability is 5%. Okay. Okay. So, and then we change it to 10%. Okay, the same degree of freedom. So here you see that okay, so here is 1, and then our degree of freedom is 0. Our degree of freedom is 5. So we have 0.15. Close it. So you see the 9.24 that you calculated, yeah? And then when the probability was 0.01, okay? Degree of freedom, still 5, okay? Go to, okay? So here is 1%, and then our degree of freedom is 5. You close the brackets, yeah? Please, is it okay? Are you getting the same thing?
Yes, Nana.
Please, let me get some feedback from you, okay?
Yes, sir.
Yeah.
All right, so good. Okay, so So let's take this second example. All right. A sociologist seeks to determine marital status divorce. Okay, so remember that we are dealing with categorical. So a sociologist to determine marital status divorced or not divorced. Men is independent of 100 men is surveyed and results are tabulated. Religious affiliations, we have A, B, C, D, and none. Okay, and then we have marital status on our left, divorce, and then others. Right. So for category A, we have a total of 211, divorce 39, married never divorced is 172. Okay, religious affiliation category B, we have 19 and 61. Okay, religious category C, we have 12 and 44. Okay, for D, we have 28 and 70. Okay, and then for none, we have 18 and 37. Okay, and then so for divorce, the total is 116. Okay, and then for married and never divorced is 384. So we have a total of 500. Okay, so for category A, we have 211, B 80, C 56, D 98, and then none. So we are required to test to see if there is sufficient evidence that marital status is independent of religious affiliation at an alpha of 5%. Okay, right. So I've sent you an Excel template. So let's have a look at it. So we'll work this with an Excel. Okay. So you have something like this. Okay. Please, have you seen a template?
Yes, Nana.
Okay. So what we have here is, I still have the same information here. Okay. All right. So we have the various categories for divorce and then never divorced. Okay. And then these at the top here, these are the religious affiliations. Okay. But this time round, we've been given the actual numbers. Okay. We've been given the observed. Okay. But we don't know the expected frequencies. We don't know the E. All right. So we'll have to derive the E. Okay. So this is where the issue of contingency table comes in. So we'll have to prepare a contingency table that will give us the expected frequencies. Okay. Okay, that will give us the expected frequencies. The first one that I did, okay, the first one that I did, you were given the expected frequency. But it's not every time that you'll be given that. Okay, so you will have to derive that. Okay, you have to derive that. Okay. All right, so this whereby the issue of contingency table comes in. So we know the totals. We know that the totals for each of the categories of religious affiliations. Okay, so we know that category A is 211, B is 80, C is 56, okay? D is 98, okay? And then this one, then none is 55, okay? So, and then the total for the divorce, remember, is 116. And then total for never divorce is 384. So we have these totals. So all that we need to do is to derive the expected frequencies for each of the religious affiliations. Okay? So what do we do? So here, all right? So here, in order to get the expected frequencies for, let's say, for category A, for divorce, for instance, okay, we multiply 211, okay, by 116, and then we divide by the total, which gives us 48.952. Okay? 48.952. Any questions about this? Another way you can look at this is that, if 500 is equal to 112, okay, therefore 116, it will give us the figure 4. It will give us the figure 4, those that are under category A. Okay, so we cross multiply, we still end up with this 211 times 116 divided by the total. Okay, so all that you need to do is that just take the total of the column, multiply it by the total of the row, and divide it by the grand total. Okay, that will give us the expected frequency for A. Okay, when we come to B, remember in terms of rows, the total for the rows here is now 384. Okay, the total for the column remains the same. So if we want the figure for the never under category A, then it is 211 times 384 divided by the total. It will give us 162.078. Please, have you seen it here? Okay. Now, let's move to category B. Are you okay with A? Category A, how we derived the expected frequencies for category A.
Yes.
Okay. Now, when we come to category B, it's the same method. Okay. So here, the total in terms of column is 80. Okay. The rows is 116384. It remains the same. All right. So we want to calculate for this side. Okay. So we just take the total of the column, multiply by the total of the row. So that's 80 times 116 divided by 500. It gives us 18.56. And that we do for never category. Okay. And also, so here is going to be 80 times 384 divided by 500. That gives us 61.44. So that's what we have here. Yeah. This one. Let's come to category C. So category C2, the total for the columns is 56. And then the total for the rows are 116 and then 384. Grand total remains the same. Okay, so if we want to check for C divorced, then it is 56 times 116 divided by 500. C never is 56 times 384 divided by 500. And that also gives us 12.9948, okay, for never. So we do the same for category D, okay? So category D2, we want to derive the expected frequencies for divorce and then never, all right? So here is 98 times 116 divided by 500. That gives us 22.736, yeah? And then 98 times 384 divided by 500 gives us 75.26. All right. Then lastly, those who are not affiliated to any religious organization. Okay, so for divorce is going to be 55 times 116 divided by 500. That gives us, for never, it's 55 times 384 divided by 500. Gives us 42.24. All right. So when you finish, you add all of them up. Okay. The rows and the columns should be equal. Okay. So here, when you add category A, for instance, you have 48 and then 162. It should give you a total of 211. Okay. So here we have derived the expected frequency. And this table is called a contingency table. All right. So once we have our O observed and then our expected frequencies, we can now go ahead and then calculate our the differences and then square the differences and then add them up to get our chi-square value. Okay, so let's move on. So here we come to get our O and then our E. All right. So we have we transport all this, yeah, or export all this, the expected frequencies and also the observed into a table. Okay, so we have for category A, okay, we have 38, 172, okay, it follows up to category D. All right, okay, and then, so we have all the religious affiliations here, and then we have our expected here. Okay, we have our expected here, and then differences, we square the difference and then divide the square difference by the expected. That gives us chi-square of 7.13. Any questions on this? On how we derived the contingency?
Nana, please, is it always the case that to derive the contingency table, the totals will be given in the observed?
Yes, so remember that whether it is observed or it is the frequency, okay, the totals should be the same. The grand total should be the same. So when a total is the same, you can have what we call the theoretical expected value and then what you actually got. So it should always be the same. The total should always be the same. All right. Other than that, you will not be able to derive the expected frequencies. It has to be the same. So if you are not given the expected, for instance, then use the totals for the actual and use that to derive the contingency. Okay. Yeah, any other? Okay. Any other? Okay. So let's go back to the question again. So the question said that our alpha is 0.05. Okay. Our say that we have our alpha is 0.05. Okay. So based on this. So So based upon this, let's go ahead and then establish our hypothesis. Okay. So we say that our marital status, okay, is independent. Okay, it's independent of religious affiliation. Okay, and then the alternative is that the marital status is not independent. Okay, in other words, there is some relationship. Okay, so the norm of the chi-square is independence. Okay, so we want to check for independence. So then the status quo is that whatever you are checking is independent, and then the alternative is that it is not independent. There is a relationship, right? So we are given an alpha of 5%. Okay, so our degree of freedom. So here, since the degree of freedom was not given to us, okay, the degree of freedom was not given to us. Okay, one way to go about this is to look at the number of columns. Okay, and then look at the number of rows, and then deduct one from each of them, and then multiply the product. Okay, so the number of columns here, how many columns do we have?
Five.
5. Okay, so we have 5 religious affiliations. Okay, so 1, 2, 3, 4, 5. So that gives us 5. So that's the column gives us 5. And then what about the categories for the marital status? How many rows do we have?
2.
2. Okay, so rows 2.
Columns or rows?
Column.
Okay.
You see? So the rows are 2. Okay, that's divorced and then never divorced. Okay, and then the religious affiliations are 5. Okay, so 2 rows, 5 columns. Okay, so 5 for the columns, it will be 5 minus 1, and then the rows 2 minus 1. Okay, so that's how you determine the degrees of freedom if it's not given to you. Okay, so please don't forget this. Okay? So it's not every time that they will tell you the degrees of freedom. Okay, so you have to look at the scenario and then be able to calculate it. So it's the number of columns minus 1 multiplied by the number of rows minus 1. So the number of columns is 5. So 5 minus 1 multiplied by 2 minus 1 gives us 4. Okay, so you go to your chi-square distribution table, and then you check probability of 0.05. Okay, and under a degree of freedom of 4. Okay, check if you get the same thing. You get the same thing I'm getting here. Check from your table. Degree of freedom 4, and then alpha of 5%.
It's the same thing.
The same thing. Okay, so this is our critical value. So basically, you establish your critical value, you come and work this. So what do we say? So here, if our marital status, therefore, if our marital status, that's if this is equal to this, it's more than the critical value, then we must reject the null hypothesis and conclude that marital status is not independent. Okay. So what do we conclude? So the observed frequency of marital status and religious affiliation did not differ significantly, okay, than what would be expected. Okay. So our problem was 7.17. Our problem chi-square was 7.14. Our critical was 4. Our critical at a degree of freedom of 4 and a probability rate of 5% was 9.94. Therefore, the variation was to be explained by chance alone. Okay? Therefore, we fail to reject the null hypothesis and conclude that the marital status is independent of religious affiliation. Okay. We fail to reject. So normally, if you are going to reject it, if you are going to reject the null hypothesis, then you say that they differ significantly. Okay? If you are not going to reject the null hypothesis, then they do not differ significantly, and then everything that happens within is as a result of chance. All the evaluation is as a result of chance. Yes, Christiana.
Hello, Nana.
Yes, Christiana, please go ahead.
Please, can you go back? Can you kindly repeat where you want to manually calculate the degree of freedom for me?
Okay, yeah. Okay. So here, the degree of freedom is the number of columns minus 1 multiplied by the number of rows minus 1. Okay. If you look at the question here, we have the columns are A, B, C, D, and none, isn't it? These are the religious affiliation. Okay, so we have 5 columns, okay, excluding the totals, all right? So 1, 2, 3, 4, 5, that's A, B, C, D, and none. So 5 columns, and also for the rows, we have divorced and then never divorced, okay? So just 2 rows, okay? So if we go by this, okay, column minus 1 multiplied by row minus 1, the columns are 5, so minus 1, multiplied by the rows are 2 minus 1, which gives you 1. So 1 times 4 gives you 4. That will be your degree of freedom. All right? So when you go into the table, you are looking for a degree of freedom of 4, okay? And 0.05, which is 9.49. So this is your chi-square critical value. So if anything is more than your actual chi-square you calculate is more than 9.49, you will reject the null hypothesis. If it is within it, then you will fail to reject the null hypothesis like we've always done. All right? Is that okay?
That means when you manually calculate for the degree of freedom, you will not subtract it by 1.
I don't get you.
You see, when the problem is given, usually before we get it from 1, we have it. You subtract it from 1. You subtract 1 from it. From the bar. And when you manually calculate it, you not take any one from it. You just use what the figure you've gotten.
No. The first example that I gave, we're talking about the dice, isn't it? Which has 6 sides. All right. We're talking about dice which has 6 sides, and then we use a degree of freedom of 5. That is 6 minus 1. Okay. Now, at that time, we're not dealing with columns and rows. Okay. So in a situation where you are dealing with columns and then rows, all right, the degree of freedom is column minus 1 and then row minus 1. So just count your number of rows minus 1 and then multiply it by the number of columns. Like if you have features, various features, count all the features minus 1 and also the number of observations, that is your row minus 1, and then multiply them. That will give you a degree of freedom. Okay.
Thank you very much, sir.
Okay. Yes, Nancy.
Yeah, Nana,
Yes.
I understand what you are saying, but it's like for the sample size we are dealing with 500 people, each person could be just one observation, right? So why are we deducting one from the column and then one from the row? Why not multiply the column by row, then deduct that product, deduct one from that product instead? Because it seems like, I don't, maybe I'm just confused a bit.
Okay, don't worry, I'll go by it. So we are looking at the number of observations, okay? We are looking at the number of observations, and then if it's just, you just have one feature, then you are fine. You just take the number of observations and then deduct one, you will get your degree of freedom, okay? But where you have a number of features added to it, okay, you count that, and then you
Other
deduct
features
one
being
from it.
added to the observations.
That is the columns. So let's say you take one observation, okay? The first column might be somebody's name. The second column might be the age. The third column might be whatever about the person. But the whole row talks about one person, okay? So you can have, let's say, 500 people, all right? So where you have a number of columns, okay, that is the way to go about it in order to determine the degree of freedom. So you were expecting that it would just be the number of observations minus one, isn't it?
Yes, but I think what you just said also makes sense, considering the observations could all be identify one particular entry from the sample.
Yeah.
So I get you. Thanks for the clarification.
So please, any other question? So let's see how we work this. So the same thing, let's go and use it in Excel. So with a blank one that I've given you, okay, so we have the, how do you call it? We have the, we have the template, okay? We have the template. So let's see how we can derive the expected frequencies for A if we were to use Excel to do it, okay? All right. So basically here, we'll be looking at, so it is the 2, 1. So if we want to get, so it's 2, 1, 1, this, okay? So it's this. So let's put this in a bracket. Okay. So we multiply that with 116, isn't it? Okay. And then we divide by the total, which is 500. Okay. So since we want to, so that gives us this. So since we want to drag this all along, okay, we can vary this a bit, okay, and then we'll let this number be the same. And then we can do the same thing here. Put this in a bracket. And multiply it by, this time around we are using this, yeah? And then we divide by the total. So, back to rest. The dollar sign, so that's it. It doesn't change. Okay. Okay, so let's move all this here and paste the value. Okay.
Hello, Nana.
Yeah.
Please, I think there is a mistake in the question. When you look at the divorced and never divorced, it's 39 and 72. But when you add this, yes, it's I think it's supposed to be 139 and 172 for the A.
Okay, yeah, okay.
Because
Okay.
it's distracting the data.
Oh, no, it must be 172.
172, okay, okay. That's my mistake, sorry. So let's add it here. Thank you. Okay, so we can just find the difference between this and that. This, then square of that. By 500. just find the summation. That's it. I think I'm getting some figures now quickly. Okay. Please, are we all getting the same answer?
Yeah, yes, ma'am.
Please, we don't want to leave anybody behind. If you are stuck, just let me know, and then I can just come. You can share your screen, and then we can all work it together. Are you stuck on anything? If I ask the question, and if you want to share your screen, we can all work it together. Okay, so once we are done with this, our degree of freedom here, so it's our columns, we had columns, number of columns, 5, isn't it? So 5 minus 1, is 4, and then the rows, 2 minus 1 is 1. So our degree of freedom is 5, yeah? Yes. Okay, so if we want to check the critical value, okay, so our degree of freedom is 5, and then our alpha is 5%. Okay, so I can write an alpha here. Alpha is 5%. Sorry, our degree of freedom is 4, isn't it? Then our alpha is 0.05. Yeah. So critical, chi-square critical. Okay, let's go to chi-square inverse. Yes. Okay, so this dialog box comes, and then our probability is 0.05, and then our degree of freedom is 4. Okay, so that gives us 9.49 approximately. Okay, so once we know this, you compare it with our chi-square that we calculated, that is 7.1. Okay, it is within range. Therefore, we fail to, it does not differ significantly. Okay, therefore, we fail to reject the null hypothesis. Okay. So basically, people who their marital status is independent. Okay? It's independent of their religious affiliation. So if you have to do this to yourself, please, any question? Anybody, everybody okay with yourself? Please. How we derive the contingency table and then went on to calculate our critical X. Okay? And then derived the degree of freedom, all right, at an alpha rate of 5%. Okay. Let's do an alpha rate of 1% and see what happens. Okay, let's do an alpha rate of 1%. $13. So here too, you will still fail to here too, you still fail to reject. Okay. What about if we do an alpha rate of 10%? Okay. So this time around, our critical will be 0.1. Our error rate will be 0.1. So we get 7.78. Okay. Even with that, it's still within range. All right. Please, are you okay with yourself? Are you okay? Can I have some feedback, please? Please. You all get the same
Now
thing?
it's okay.
Yes, sir.
Okay. Good. All right. So our observed frequency of marital status and religious affiliation did not differ significantly, okay, than what would be expected theoretically, okay, at the degree of freedom and then the number 500, okay, which gives us 7.14. Okay. So our problem chi was 7.14. Our critical chi value was 9.49. Therefore, the variation was to be explained by chance alone. Therefore, we fail to reject the null hypothesis and conclude that marital status is independent of religious affiliation. So please, when you're try as much as possible, when you're giving the result, to state it technically like I've done. Okay. Any question? Any question? Any question? So basically, so let's look at our key points. So chi-square can be thought of a test of independence. Okay. So here we're looking at relationship between categorical variables, whether they are related or they are not related. Okay, so the null hypothesis is that the two categorical variables are independent. Okay, the alternative is that the two are related or they are not independent. Okay, so is the observed variation between observed and expected frequency minor enough to be within what we may expect due to chance alone? Okay. All right, so we also look at contingency table and also degrees of freedom. Okay. Any question? That's about it for chi-square. Any question? Any question?
No.
Hey. So just give me 1 minute and we'll discuss our assignment. What's today's date? Today is 29. Okay. Sorry, I was having some challenges with my internet. Can you all hear me, please?
Yes, sir.
Okay, all right. So let me just share our assignment. Okay, so this is your assignment brief. You're supposed to please, this constitutes 40%, okay, of your overall marks for mathematical foundations. Okay. So as always, the deadline is 31st, okay, March. Okay. Like I always say, you can take the time you want to do it, but please don't go beyond the deadline because there's a penalty for it. Okay. So up to 1 week after the deadline, we get 20 marks deduction. 2 weeks, 15 marks. Beyond 2 weeks, it will not be accepted. Okay, because we've got to submit our results within that turnaround time. Okay, so please don't go beyond that. All right, so you have this question. Let's go through it quickly. So the scores of a standardized test are reported to be reported by the testing agency to have a mean of 70 based upon this personal observation. A school guidance counselor believes the mean score is much more higher. Okay, he collects the following scores from a sample of 50 randomly chosen students who took the test. So basically, this is about hypothesis testing. Okay, so conduct a test of hypothesis at an alpha of 5%. Okay, so you know the routine. Okay, when you are done, determine the 5th and then the 75th percentile. Okay, and see if there are any outliers in the data. Question 2. The manager of an advertising department has asked a creative team to propose 6 new ideas for an advertising campaign for a major client. She will choose 3 of 6 proposals to present to the client. Suppose the proposals are A, B, C, D, E, F. In how many ways can the manager select 3 proposals? Okay, it's unlikely that the manager will randomly select 3 proposals. Okay, but if she does, what is the probability that she will select A, D, and E? Okay. 3, explain the concept of multiple linearity and homoscedasticity regression analysis. Okay, and then the average score of 4 golfers for a particular course has a mean of 73 and a standard deviation of 3.5. Suppose 49 golfers played the course today. Find the probability that the average score of 49 golfers exceeded 74. So assumptions of logistic regression, okay, whether missing data or outliers will be affected by the model. And 4, a survey performed at a car show found that 52% of the respondents were women, 48% were men. The results also showed that 70% of the women favored small cars, whilst only 40% of the men favored small cars. The poll results are summarized as follows. The probability of a woman being a woman is 0.52, man 0.48. Favor small cars, given that the person is a woman, 0.7. Favor small cars, given that the person is a man, okay, 0.4. Compute probability of woman and favor small cars. Probability of man and favor small cars. Probability of small cars, favor small cars. Probability of woman giving favor small cars. Probability of man giving favor small cars. Okay. Then the last one. The data below shows the age and favorite types of music of 779 randomly selected people. Test to determine whether the age and preferred music type are independent. Okay, so here you're using an alpha of 0.05. So you have the age and then the type of music. State the null hypothesis and also the alternative hypothesis. Create a contingency table for the data. Perform a chi-square test to determine if there is any evidence that age and preferred music type are independent. Okay, so just answer any form. Okay, answer any form. Okay. Any questions? But I will advise you to try all the questions. Okay. All right. A word to a wise is enough. Any question? Any questions, please, on what we've done in this program? Anything you didn't understand? But today, everything we've done today, is it okay? Are we okay?
Yes, Nana.
Good, good. All right. Any question? Any other question? We are wrapping up. Any other question? Any other question? Any other question? What? Yes, Muslim.
Okay, so now what I wanted to ask is concerning the confidence level or the alpha. In our practice,
Yeah.
let's say we are done with the course and we are working on a data set. Those values, are we the ones going to assume it? Or
Normally, yes. Normally, every industry has its own standard. Okay. I think I touched on it the other time, especially in the health industry. They don't give so much room for error. So normally you will see that the probability for error is like 1%, because giving a probability room for 5% might be fatal. Have you seen? And so normally in business, you will find that you normally use 5%. So it depends upon the industry you are in. Okay. But the main thing is that whatever thing you use, just let everybody know that these are your assumptions. Okay.
Okay, thank you.
Any other issue? I will send you the assignment. Okay. All right. Thank you very much, guys. It's been a very interesting journey. So I will see, God willing, I will see you when we come to predictive analytics, and then we'll see other aspects of R. Okay. That it will be so exciting. I can't wait to have you on that course. So if you have any issue, please do not hesitate to get in touch. Okay. I prefer that you send me a WhatsApp or email. That way, if you miss me, I can always get back. But if you call me, it's most probable that the time you call, I might be busy, so I might not be able to have much time with you, but if you drop me a mail or something, I'm sure to get back. Yes.
But sir, I sent you WhatsApp asking question. I haven't received any reply.
Christiana, please, when you send a WhatsApp, please introduce yourself, okay? If you just send, it might be difficult, so please introduce yourself and then, what was it about? But I never said anything, so I didn't know. Sorry about that. It wasn't deliberate.
I wanted to find out how you change an object. I've forgotten. There are a lot of questions, but I asked one. Assuming if you replied, I'll ask the next. But
oh, okay. Why didn't you ask all of that? Oh, Christiana. Okay.
The data I picked for the R project, actually, I'm having it difficult.
So what do you intend to do? You want to change an object?
Yes.
What do you mean by want to change an object?
I plan changing everything, actually.
Changing your data, your data set.
Yes.
Yeah. Go ahead and change it. You are at liberty to do it. Okay. If your data is not working out well, you can always change it. Okay.
Please, do you always need the current one as you specify, latest by 5 years, or we can just pick any?
No. I'm not restricting it to any data set. Okay.
So we can take the default R data to
no.
Any of them.
I want you see the import of what I wanted you to do is don't just go and take any data. I want you to take something that you think might be challenging. Remember, at the end of the day, you have to prove that you are an accomplished data scientist. Okay. So don't just go and take any data. No. So that's why take something that you think that okay, this is in my industry. I would like to know more about this. What can I do with this data? Okay. Use that first. And I mean, at the end of the day, if you're able to do something very good, you'll be so proud of yourself. How do you think? So don't think too much about the marks that you are going to get. It's much more about the what you've learned so far, how you can apply the skills to world problems. Have you seen? Okay, how
all
you
right,
can,
sir.
yeah. So don't just keep any data and then you get the marks and then you have nothing to show for. Yeah. All right.
All right, sir. Thank you very much.
Is any other issue? All right. So like I said, you can always get in touch. Okay. If you call me and you don't get me, just drop me an email or WhatsApp. I will surely get back to you. Okay. Just let me know who you are, and if you just call and then I don't call back, probably I get a lot of calls. So if you drop an email or WhatsApp that it's you, blah blah blah, I'll find time and call you. Okay. All right. So thank you very much once again, and have a very lovely evening. And hopefully, I will see all of you very soon. Okay. So take care. Bye bye.
Bye, Nana. Thank you too.
Okay. So I'm here for the
Bye
next
bye.
5. If you have any issue, you can let us discuss. I'm here for the next 5 minutes. Okay. Take care. Bye.
Please, sir, if you are here for the next 5 minutes, can I ask my question?
Yes, Christina, of course.
Please, I lost you when we were calculating the last part of the Excel with the alpha.
Okay.
Yes. And frankly speaking, I wasn't practicing along because of where I'm currently at. So if you can explain to me.
I've sent the templates to you.
I have it. It's
okay.
opened on my machine, but I was not typing that when we were
so
working.
You type when you make a mistake and you are stuck somewhere, then I explain. Okay.
All right, sir.
All right.
Right.